Hey Kata, wanna see how the sausage is made?
Uh, Weird. Wait, is this our OnlyFans channel?
We don't have one.
Uh, okay, I'm a bit confused then. Should we have one?
No, I was talking about C++ coroutines.
Okay, that's weird.
Okay, let's start from the beginning. Okay, so this is where we left last time. So,
Okay, nice, nice,
so
nice, nice. Yeah, show me the main.
okay, but
This is
if you
not
didn't
here. We
watch the
are in the
last
main last
episode,
time.
please go and watch it right now. We're gonna leave the link here.
Okay.
Otherwise, it will not make a lot of sense.
But I expect that people see the last episode. I hope.
Yeah.
Please
Okay.
see our episodes.
Okay. So
So there is
here,
the main.
here is the
Okay.
main, and
Okay.
so
There
you
is
see
some
that
magic.
yeah, here's the magic. So we have this pledge context, which with this run method, which is what provides the capabilities to all the pledges to schedule work for later.
Uh, okay, I have a question.
Yep.
Is shared across all the function? Did you use a global variable?
Uh,
That's you.
um, it
I
depends.
hope.
It's not global, but
Okay.
yeah. Okay, so I'm using a thread local. I know I feel dirty for doing that, but
Yeah.
just to give
It is not so
context,
dirty, I suppose that it's useful in this case, but this is not a keep it clean episode, so I can pass it. You can
okay.
pass on it.
So just to give the TLDR, a thread local is a variable with thread storage, which means that every thread gets its own instance of this variable, and we are saying here that by default this is null. And what we're doing is that when we go and we build a pledge context, we register ourselves as the context of this thread. And when we destroy it, we unregister ourselves. So these objects are expected to be used on the stack, are expected to be used inside the function
Yes,
during the execution of a single thread.
makes
And
sense.
what they
About the
do,
real implementation?
yeah,
Yeah,
the TLDR is this provides the equivalent of the JavaScript event loop. So you can see
you
down
have read the
here,
wheel.
yeah, I have invented the wheel. So what it's providing is a list of tasks, which is equivalent of the micro tasks in JavaScript, and a list of awaiting. But it's not a list; it's a number of awaiting resolution, which is work, asynchronous work that is there, and is waiting to terminate. So
Okay.
when you call run, it just picks up all the work that has been registered so far, and it goes through all the microtasks. If new microtasks get added, it just keeps going. When all the microtasks are done, it just waits for either more microtasks or for when there is no more asynchronous work. So if there is
Okay,
no
makes
more
sense.
tasks, and if there are no more tasks and asynchronous work waiting for, we are done, and so we can just
To the
finish.
application. Yeah, perfect.
So let's move to see how the pledge actually used this.
Yeah, here
Uh,
is interesting to see how you made
okay,
it.
so pledge. Well, first of all, we made the
Let's do
pledge.
new.
Yeah, I'm pledging. Uh, the pledge is movable and copyable, so it behaves like a shared pointer. And in fact, if you go and take a look, it's actually a share pointer. And we
Yeah.
have an implementation, which is just a purely virtual interface. We're going to see this later. And we have three implementations of this interface. And the idea is that we have one for the already resolved case, we have one for the callback implementation, we have one for the coroutine implementation.
Okay,
And
but one step at a time.
let's focus on the coroutine.
Exactly.
The contract of a type that can be
Oh,
used as return type for a coroutine,
you use a
it's
promise. You use a promise.
yeah, that's why we didn't call them promise, because
Ah,
the
okay.
type needs to have a type defined inside of it, which is called promise type. So you didn't want to have a class called promise, which contained a type called promise type.
Yeah, it could be confusing. Yeah.
Yeah,
Ah,
so pledge it
okay.
is. So
I forgive you.
this is step one. Your type contains this. Your type contains this inner type,
Okay.
and this type needs to follow its own contract. And so we're going to define this part here. And if the contract is larger, there are other stuff that you can implement for other features. But for what we need
Mm-hmm.
and the capabilities that we implemented, we just need this five, which is coroutine object. Get return object. What this
Yeah.
does is
Easy.
that when the coroutine starts, this object gets constructed, and this function needs to convert from this type to the return type of the coroutine. So in this case, we are just providing a reference to the promise type itself and just passing it to a pledge. We are going to see later what this is doing. Then we have initial suspend and final suspend. This is used by the coroutine system to decide what to do when it starts and when it ends. So when it starts, you have two options. You can either, well, multiple options, but there are two that are simple ones, which are suspend always and suspend never. With suspend always, when the coroutine starts, before actually starting, it's going to get in the suspended state. With never, it's going to move. So in our case, we want the suspend always because we want to enqueue the work inside our pledge context. And then we have suspend never on the final, because when the coroutine ends, we don't want to manually have to delete stuff. So we just let it go. So when it ends, everything gets deleted and the promise type gets deleted with the rest of the coroutine.
Okay.
Then we have return value. The return value is the counterpart of coreturn. So
Okay.
when the coroutine calls coreturn, this function
It
is
ended by
invoked.
this one.
Exactly.
Perfect.
So what we're
And
doing,
you move it because you're using a shared pointer.
yeah, well, we are moving this one actually because it's we are assuming that the type is movable. And so we're just taking the result and moving it into the implementation. Yeah. And this implementation is not part of the contract. This is the coroutine implementation of our pledge.
Yeah. Okay.
So it's there.
This makes sense. It's easy to move. Yeah.
Yeah. And we are just calling on our implementation this return value. So we are just forwarding the call. And then
also,
we have...
you see that yeah, I like that, but you have to implement it. So it's something that we can do to handle, I don't know, the catch.
Yeah, exceptions, but
something
not
for
today. Yes.
Yeah.
So you can have another episode in which you talk about exceptions.
I like it.
And yeah, we can talk about probably other ways to handle this. We could be, instead of having actual exceptions, you can go with an STD expected to have a more explicit error handling system, but for a later time. So this is the bare minimum you need to implement.
Okay. And
now there is the other part, which is the coroutine part. But we want to make this awaitable, right? Because we want to allow a pledge to be awaited upon. So this is where the awaitable contracts get into play. And again, the contract is larger. There are other features in there, but what we care about specifically is await ready, await suspend, await resume. And specifically what they do is await ready tells the coroutine system if the awaitable is already ready. So if it needs to actually suspend. So if this returns false, if this returns true, it will not even stop, it will just move forward. If instead it returns false, so it's not ready, it's going to call await suspend. and it's going to pass you a coroutine handle, which is a type erased coroutine handle. And this can be used when this pledge is ready to restart the coroutine that is awaiting on it. So this can potentially, if you have multiple coroutines that are sharing the same pledge, you could have this being called multiple times before it's actually fulfilled, or you can have multiple times in sequence. So it depends on the case. And so what we do is that we take this handle and we register it in our implementation.
Perfect.
When everything is done, well, even when we were already ready, or when we get ready and we resume, the system is going to call await resume. And the responsibility of this call is to return the value. Exactly, the value that that was it was expected there.
The main scope of all of these. Okay.
Yeah, that's it. Nothing more. So now let's move and see how this awaitable interface is actually implemented. Because I mean, here we are effectively just forwarding to something else. So if we see our implementation, it's these three functions: has value, value, add awaiter.
Okay, the one you showed before. Yep.
Exactly.
Perfect.
So let's start from the easiest version, the one that actually we built here, which is if we build one that is already resolved, we create a resolved implementation. So that is the easy case. So the resolved implementation has a value, has value returned true. So effectively, we will not wait here. We just go through.
Yeah. And the value is the result that you pass to the function.
Yeah, everyone is happy. The value is provided is that one, and we do nothing for add awaiter because we're never going to call this function. It's there just because we need to implement it.
It's so clear.
Then let's move to the coroutine version. In the coroutine version, what we're doing is that we are storing the value in std optional because until we actually have the value, we don't know which one it is. So what we do is that we can check if the value is there by checking has value. We can check, we can return the value, so result of value. We can add awaiters, and we are just storing them into a vector of handles.
Yeah, makes sense.
And so we just put them in the queue, and then we implement return values. If you remember, the return value up here was forwarding the call to the implementation. So what we end up doing here is that we store the value in the result. We get our pledge context, and we add a task in the queue because we want to do this later. We add a task in the queue where we get all the awaiters, and then we resume all of them one at a time. So effectively, if you had one, we're going to resume one. If we had none, we just store the value and leave it there. If we have many, we go and we resume all of them. So effectively, if you have a co-wait and that co-wait was called after it was already fulfilled, it's just going to return true here, gets the value and moves out. If instead is not yet fulfilled, we'll call add awaiter, and when we get here, we're going to wake up the other pledge or the other coroutine that was waiting on it. And the implementation of the callback version is practically the same. So again, we have an std optional, we have a vector of awaiters. Just a moment. Nothing.
A few minutes later.
A few minutes later? Actually, no, if we're a few seconds later, I was confused. Sorry, nothing. So again, we get here, we get our handles, we put them in the queue, and when we have our resolve, we go and we schedule a macro task, and we put our information in there. The only tricky part is that in the callback version, which is effectively this one, we are building our callback implementation, and this gets forwarded down here where we go and we effectively schedule the body already
Okay.
on the so we schedule a body on the context, and then we make sure that the result gets fulfilled again on the same context. So they capture the context when we
Yeah.
start the body, and when this is the implementation of the resolve. So we effectively make sure to reschedule all the work on the same thread where we started, even if the resolve is called on another thread, because we don't want to
Yeah.
start scheduling work on random threads all around the system. So this is just
Yeah.
push us.
Probably. Yeah, probably we can make an example on GitHub about that so the folks can
Yeah,
dig
well,
into more.
we technically already have one, which is set
Yeah.
timeout, which
Oh.
is set timeout is here. And I mean, we are not going to details. This is actually starting a thread. So when this resolve, well, this callback is called, it's technically on
Yeah,
another thread. So we don't want to accidentally start scheduling work here. We
absolutely.
want to move it back to the main system. And
Okay.
we are halfway through the file. Why? Well, because we have the implementation of pledge void. And we can go really fast inside of this. The only difference
Yeah.
is this one. Instead of return value, we implement
Okay.
return void. That's it. With and all
Okay.
the difference in these two implementations is that in the void version we don't have a return value. So instead of return value, we call return void. The implementations don't need to store a value. They just need to store if it is done, because there is no value, and effectively it's the same thing. The all
But I think
waiter.
that I think that our friends becomes to get hunger. So
Yeah, and I think
probably
this is most
yeah,
of it. And
yeah.
so
We
what
could
can
make a
we
web
do?
server. Yeah.
Yeah. What can we do later? We can do something more. We can go, and there are other facilities that we could implement with coroutines. For example, generators, the generator functions in JavaScript, or even more complex multi-threaded systems,
Yeah.
or a web server or something.
Yeah, I know
But
that you like that one, so I see. I spoiled it previously, just a little. What do
yeah,
you say? I know
but
that you like it.
yeah, we are out of time for today. So
Yeah. I think it's time to go.
see you next time, folks.